Okay, so welcome everyone. We are starting our third week with the lecture by Chris about n equal to superconformal field theories. Please.
Thank you. Let me just get something figured out. Okay. Thank you, Slava, and thanks again, everyone, for coming back for part 3 of this. So last time we took this long detour into the formal mathematical axiomatics of vertex operator algebras. And now for the last lecture, I want to come back and look with a little bit more, look in a little bit more detail at the sorts of structures that show up in the vertex operator algebras that come from 4-dimensional n equals 2 SCFTs via this cohomological construction that was the subject of the first lecture. So if we get through everything, we're going to run through some sort of immediate, basic, if you want, properties of the vertex algebras that come out of this construction. I'll gesture towards some examples where we have some sense of what the vertex algebras are that arise in this way. I'll talk about one example in a little bit of detail to motivate a couple of more advanced topics, as it were, having to do with moduli spaces, Higgs branches, and also with unitary, because we imagine that the 4-dimensional theories we're starting out with are unitary theories. So here's what we had in the first lecture. Schematically, we had some construction. We start out with a 4-dimensional n equals 2 SCFT, and there's a cohomological operation where we reduce the vector space of local operators and define some fancy way of moving operators around in 2 of the directions inside of R4. And we get a vertex algebra, which, just to take advantage of the formalization that we had in the last lecture, let's look at the 4 ingredients that go into a vertex algebra. We have a vector space of local operators, which coming out of this construction were the so-called Schur operators. So these were local operators that were characterized by a couple of linear relations on their quantum numbers that we saw before. Already I can point out that I was a little bit too lazy last time in how I formalized things, because the conformal dimension that I get out of this construction, the H quantum number, which is what the holomorphic SL2 in the plane sees, if you take advantage of these relations, you find that it's equal to this combination 2 times the SU2R charge plus the sum of the spins, which in general is a half integer, a non-negative half integer rather than an integer. So I didn't say it last time, but there's a fairly gentle generalization of the axioms that I gave for vertex algebras last time, which gives half Z graded instead of Z graded vertex algebras. So you allow operators that have half integer grading, but you still only allow integer powers of Zs in the OPEs. So this gives you some sort of selection rule based on the parity of the conformal dimension. We're supposed to have a privileged state in the vector space, which is the vacuum, and that's just going to be the identity operator in the Schur sector. We had a unfortunately named translation operator, which was called T, which just is something we're inheriting directly from 4 dimensions as the holomorphic translation operator or holomorphic momentum operator in these Z bar coordinates. And then the hard work was done by this procedure for building a field that we called Y in the vertex algebra axioms. And the way that that's done is this sort of elaborate, twisted, translated construction that I gave, where you take your sure operator, you move it away from the origin, but then you correct it with various non-highest weight elements of its SU2R representation, accompanied by explicit powers of Z bar. And this parameter zeta I've been carrying around just for fun. And then it was a result of this analysis of the superconformal algebra. The thing that you get if you take this object and do OPEs and restrict to the level of cohomology classes with respect to this supercharge is something which is going to be meromorphic, and so that we can think of as one of these endomorphism of V valued formal series in Z and Z inverse. Okay, so that's bringing us up to speed on the connection to the rigorous formulation of these things. In practice, we're maybe less concerned with all of these axioms and more concerned with what we're actually getting out of this procedure. So if you're given a four-dimensional SCFT that you understand to some degree, greater or less, depending on how it's showing up in your life, we should want to know what things we can say maybe right away and what things we can say after a little bit of work about the vertex algebra that comes out of this procedure. Okay, so the first thing is fairly immediate. I meant to get to it in the first lecture, and in fact, I flashed a slide, but I didn't talk about it. And that's that you necessarily get a Virasoro subsector, if you will. And so we're actually talking about vertex operator algebras in this idiosyncratic terminology from last lecture, where you add the word operator when you have a Virasoro subsector. And this comes appropriately enough from the fact that in a local 4D n equals 2 SCFT, we expect to have a stress tensor, and that thing necessarily lives in a particular supermultiplet, which is the so-called C hat 0, 0, 0 multiplet. And that thing contains a unique SL2 primary sure operator, which is a specifically chosen component of the SU2R current. It's the SU2R highest weight. And you have to choose plus dot polarizations for the spin. So this is the vector with sort of a Z index for its spin. And then you follow your nose, you build the vertex operator associated to that via this twisted translated operation, which is going to look like some unwieldy mess like this. And then you want to take the OPE. And of course, in general, we don't have complete control over the full OPE of operators in a CFT, but what we care about is the occurrence of certain sure operators in the OPE of this thing with itself. And those turn out to be sufficiently constrained by superconformal ward identities in 6 dimensions. So there's some technical calculations you have to do. But you can work out that up to Q exact things, you're going to get exactly an OPE that looks like the Virasoro OPE, the Virasoro vertex algebra OPE, where the key ingredients are this term, no cubic term, and the term that you get over the quartic pole is determined in terms of the C-type Lyell anomaly coefficient in 4 dimensions that I've called C4D. And if you compare this expression to the canonical Virasoro vertex algebra OPE, it fits the bill up to a relabeling of coefficients where this C4D gets related to the C central charge of the Virasoro algebra with a factor of -12. So in the usual Virasoro algebra, you would have C over 2 in this place instead of -6C. And so this is an interesting entry in our dictionary already, because in a unitary four-dimensional theory, the C-type Weyl anomaly coefficient is always non-negative. It's always positive, in fact. And so the Virasoro central charges that we're going to get out of this construction are always going to be negative. So we're getting Virasoro algebras that look a little bit non-unitary from a more conventional 2D CFT point of view. An important further technical fact that one wants to be the case is that if you take the modes L plus minus 1, L0, that you would infer from this stress tensor operator that we built in a sort of fancy way, we would hope that those things will actually act on Schur operators the same way that the intrinsic SL2 symmetry that we had in the plane acts, because we want this Virasoro to somehow be the sort of Virasoro that you get when you enhance ordinary global conformal symmetry. And this is the case. This is, again, something that requires some sort of selection rules in an OPE, but it's all because of the fact that we're working within the stress tensor supermultiplet. So sort of the action of this Virasoro operator, even though it came from a sort of funny place, it all traces back to the underlying conformal symmetry of the theory. Okay, so again, to make contact with our terminology, that means that the vertex algebras that we're getting are actually vertex operator algebras. And in fact, they are what I called vertex operator algebras of CFT type last time. Remember that that means that they have weight spaces starting at 0. The only weight 0 operator is the identity operator. And at positive weights, you have finite multiplicity. I haven't proven that you have finite multiplicity, but it's not a hard argument. And I'll leave it as an exercise. There's another thing that I was being a little bit too lazy about last time, which is that I worked entirely in the language of bosonic vertex operator algebras, where all of the operators have commutation relations. In practice, Schur operators can be fermionic as well. In fact, whether they're fermionic or bosonic is tied directly to their U1R charge. If they have integer U1R charge, then they're bosonic. And if they have half integer U1R charge, they're fermionic. That ties back to the relation between U1R and J1 minus J2. So being even more accurate, we should say that we're getting vertex operator superalgebras of CFT type. And okay, I didn't write down the axioms for these things when you add the super, but hopefully as physicists, we all have a sense of how you add minus signs and turn commutators into anti-commutators when you introduce fermionic degrees of freedom. It's a perfectly healthy generalization of the structure. Another comment, which maybe sort of goes hand in hand with the apparent sort of lack of obvious unitarity that we got when we had a negative C central charge, is that there isn't a spin statistics theorem at work here. So if you had a vertex algebra showing up in a healthy unitary two-dimensional conformal field theory, then operators with half integer conformal dimension would be fermionic, and operators with integer conformal dimension would be bosonic. But in our case, there's no direct correlation. So for example, we had these B hat multiplets, which can perfectly well be integer or half integer conformal dimension, and those things are always bosonic, just by virtue of the four-dimensional supermultiplet. And you can look at the rest of this classification due to Dolan and Osborne, and figure out where the bosons are and where the fermions are. And it's not correlated with integrality. Okay, so generally we're a little bit in the woods with these vertex algebras compared to what you will have spent your life running into if you come at this stuff through two-dimensional unitary CFT. And a final collection of points is that by selection rules, and this time I'll spell it out a little bit, if you look at the OPE between the stress tensor in the vertex algebra, which again is this element of a C hat 0, 0, 0 multiplet, and the SL2 primaries in any of these B hat D or D bar multiplets. So these were sort of, if you want, the B hat D and D bar multiplets are the least generic, they're the most special of the Schur operator multiplets. The generic thing was these C hat multiplets. So those things are always going to be Virasoro primaries. So not only do we have a Virasoro subalgebra, but we have some sense of how things are structured in terms of the action of that Virasoro algebra. By Virasoro primaries, we mean that the LNs, the positively graded Ls, annihilate these operators for n 2 and above, which means that the quartic and higher poles in the OPE between the stress tensor and those operators vanishes. And just to give sort of a flavor for how these arguments go, you don't need a fancy selection rule argument to see this. You can do it just by thinking about charges under global symmetries. If I assume that I have one of these B hat D or D bar type of Schur operators, I'm going to just call it O. By virtue of it being in one of those non-generic multiplets, its chiral algebra dimension, H, is given by the sum of its SU2R charge and the magnitude of its U1R charge, whether that's a plus or a minus, depends on whether you have a D or a D bar. If you had a B hat multiplet, then U1R would be equal to 0. And then you're hitting that thing with the stress tensor, which we saw how it was built a moment ago. But remember that in the full four-dimensional setting, that stress tensor is a superposition of different components of an SU2R triplet. So this T you should think of as something which has H equals 2 under my holomorphic SL2, but it really has SU2R charges equal to +1, 0, or -1, depending on which component in the expansion of that operator you're looking at. And then I want to look at what sorts of singular OPEs could show up on the right-hand side. And if I just write something constrained by SL2 covariance, I'm going to have some operator appearing with a Z to the H1 plus H2 minus H3 in the denominator. H1 is 2, H of the stress tensor. H2 is what I just called H here. And H3 is whatever the H of this O3 is. And then, oh, sorry, didn't mean to zoom in. And then we can start just imposing charge conservation. So this operator, oh no. Apologies. There we were. So by SU2R charge conservation, this operator O3 is going to have an SU2R charge R3, which is the R charge of this guy that was sitting at the origin that had definite R charge capital R, and then either +0, +1, or -1, depending on which term in the expansion of T is leading to this term in the OPE. Its U1R charge is just going to match that of this operator because the stress tensor carries U1R charge 0. And then if I use these linear relations that I get for Schur operators, its SL2 conformal dimension is going to take this funny form. It depends on what the gamma was here that appeared in the SU2R charge. And then it sees the U1R charge and also the minimum of J1 and J2. Whether J1 or J2 is the smaller number is correlated with whether UNR is positive or negative. And then if you plug that all in, you get a pole of this order where J1 and J2 are non-negative and gamma is +1, 0, or -1. And so you see that you just simply by conservation laws, you can't have a pole of order bigger than 3. And so you can't have the sort of quartic and higher poles that would tell you that you have something which is not a Virasoro primary. So Okay, that was a little bit of detail. Maybe it was still a little bit fast. If you're a person who's trying to learn about this stuff, I would encourage you to think about this calculation, because a lot of the interesting structure in these vertex algebras has to do with what happens if you sort of ask a reasonable vertex algebra question like this, and then go under the hood and ask what happens when you sort of disentangle things into these actual twisted translated operators that see the SU2R charges you had in 4D and impose some selection rules. And a conclusion that we get that may or may not sort of change our perspective, a conclusion that we get is that if we have a four-dimensional theory that has a non-trivial Higgs branch, so the dimension of its Higgs branch is bigger than 0, then remembering that we get B hat operators corresponding to all of the algebraic functions on the Higgs branch, of which there will be infinitely many if the Higgs branch is a positive dimensional algebraic variety. This means that we'll get an infinite number of Virasoro primary operators necessarily. So if we were hoping that we were always going to be running into things that sort of vaguely looked like Virasoro RCFTs, not that you should have hoped that, but you could have been really optimistic, and you're not going to be lucky. You're going to be dealing with things that have a lot more structure than just the Virasoro algebra. And more generally, via a similar selection rule argument that I won't spell out this time, the generators of the Higgs branch chiral ring, remember that the Higgs branch operators form a commutative ring, which is the Higgs chiral ring. And the generators of that, in the sense of generators of just some finitely generated commutative ring, are necessarily strong generators in the sense that we reviewed last time. So that means that these things don't arise as normally ordered products of any other operators in the vertex algebra. This is not it's not exclusively the case, so there can be other operators that also give you strong generators, but the Higgs branch generators definitely do. Okay, so that gives us, we're starting to get some intuition for what sorts of structures are showing up. We get some Virasoro structure and some organization according to that. We get an analogous story when there are continuous global symmetries in our four-dimensional theory. So there's an avatar of a continuous global symmetry in the operator algebra, which is a so-called B hat 1 multiplet, which is the multiplet that contains the conserved current. And in the B hat 1 multiplet, the Schur operator is the superconformal primary, the so-called moment map operator. So it's a scalar operator which lives in the adjoint of the global symmetry group. So this capital A is an adjoint index. And just like we did with the stress tensor, you build some object that makes sense in vertex algebra world, which we're going to presciently call JA, which again has three components because the B hat 1 superconformal primary is an SU2R triplet. So when we do this twisted translated expansion, we get a Z bar term and a Z bar squared term. And once again, because this is a operator that has some connection with more conventional four-dimensional symmetries, we have some control over its self-OPE in terms of word identities for that four-dimensional global symmetry along with superconformal symmetry. And if we choose normalizations correctly, then we get something whose OPE, again, looks familiar. It looks like the affine version of that four-dimensional global symmetry. So there's a nice sort of story that emerges over and over again, where we have some sort of symmetry structure in 4 dimensions, whether it be conformal symmetry or global symmetry. And then at the level of this associated vertex algebra, you get the sort of natural affine vertex algebra version. So this is an affine current vertex algebra associated to the same Lie algebra or Lie group, where again, there's a bit of a translation. There's a quantity called K4D here, this is what people sometimes call the flavor central charge. It's related to a global symmetry, R symmetry, a 't Hooft anomaly in your four-dimensional theory. And it appears here with a particular coefficient. So you get minus K4D over 4. And if we were studying a canonically normalized affine Kac-Moody vertex algebra, the thing we would have here would be K over 2. And so there's a relationship between the level K of the affine Kac-Moody and the flavor central charge K4D, which is given by this, which again includes a minus sign, which once again is some push towards non-unitarity, because in four-dimensional theories, the flavor central charge is always positive in a unitary theory. And again, in ordinary two-dimensional unitary conformal field theory, K would also be positive. So here we're getting non-unitary structure. And I won't run the same sort of narrative more times, but you get an analogous story in the case when your four-dimensional theory has more supersymmetry. So if you had a four-dimensional theory with n equals 3 supersymmetry instead of n equals 2, then you would have some extra supercurrents living in D and D bar multiplets, and running the same story, you're then going to find that you get a super Virasoro algebra in the vertex algebra world, n equals 2 super Virasoro. So that includes a U1 R symmetry that lives downstairs in the vertex algebra. And in the case where your four-dimensional theory has the maximum n equals 4 supersymmetry, then you get what's called the small n equals 4 super Virasoro VOA. I won't write it down, but it's the one that people maybe are the most used to if you've spent time with n equals 4 SCFTs in 2 dimensions. Okay. So that's getting us more structure. In fact, I should emphasize this is not a sharp statement, but this is a heuristic statement. Having sort of affine subalgebras like this under control, knowing that you've got affine Kac-Moody vertex subalgebras and Virasoro vertex subalgebras with given levels, that frequently puts a lot of constraints on what the rest of your vertex algebra can look like. And so even though we've only looked at a couple of operators and done or reviewed a detailed analysis, because vertex algebras obey these very strong associativity conditions, we're already getting pretty far. And finally, I should mention, although this won't play a role in the rest of these lectures, that in four-dimensional SCFTs, there's a very popular thing to compute, which is the superconformal index. Oftentimes, this is under pretty good control, even in theories that we don't have very convenient descriptions of otherwise, due to hard work by many people. And there's a limit of the superconformal index. So this is the path integral on S3 times S1 in your four-dimensional SCFT that gives you a supertrace over the radially quantized Hilbert space. So it's giving you some sort of operator counting function. And the so-called Schur limit, this is where the name Schur operator comes from for these operators we've been discussing, which is written this way. There's a conventional term here, which has a factor or has a fugacity beta. Turns out that the answer is independent of beta. So this is just a regularizing factor. And other than that, you count local operators with powers of q to the e minus r, along with x's indicating charges under global symmetries. And in this limit, when you write your supertrace this way, you get something which ultimately only counts the Schur operators. All the other operators cancel out. And so we can reinterpret this as something which counts up to signs, because there's a supertrace here, something that counts the the elements of our state space for our associated vertex operator algebra. And in the world of vertex algebras, this is what you would call the vacuum character of the vertex algebra. This is just a straight up translation where instead of saying that you're tracing over the Hilbert space of an SCFT, you're tracing over the state space of your vertex algebra. And instead of E minus R, you have L naught, but those were the same for Schur operators. And there's even this funny little factor of minus C over 24, which is conventional in the 2D CFT world as sort of a Casimir energy that's important for modular transformations. And there's an analogous Casimir quantity that appears in 4D, which is also important for some nice transformation properties. And they match. So C4D over 2 is the same as minus C2D over 24, using this dictionary we had before between C4D and C2D. So although I won't be presenting arguments that hinge on understanding Schur indices, this is an important entry in the dictionary in general, because quite frequently, I'm repeating myself, but quite frequently, in theories that one might not know a whole lot else about, one might have access to this quantity. And having the vacuum character, which is a whole infinite Q series, is quite a lot of information to have about a vertex algebra. If you have a proposal for a characterization of the vertex algebra associated to some theory, and you can go and compute the vacuum character and compare it to your Schur index that you got from some friend who's good at localization calculations, then you're going to have a good sense of whether your guess is correct or not. Okay. So that's all sort of generalities. Now I just want to mention a few actual examples where via various arguments of the type that I've mentioned and maybe otherwise, we have a good sense of what the associated vertex algebra of some theories are, just so we see, what actually comes out of this machine in examples. Of course, there are many examples. There are lots of different classes of four-dimensional SCFTs. So this is not really meant to be genuinely representative, but I've tried to list some examples that show some of the range of types of vertex algebras that you do run into. So for people in the audience, if there are any who are not lovers of four-dimensional n equals 2 SCFTs, don't worry too much about the characterization of these theories on the left-hand side. I just want to show sort of what part of the vertex algebra world we're populating via this map. So there's a class of Argyros-Douglas SCFTs that are sometimes given this double Lie algebra labeling. And in that case, it's the A1, A even theories, which are probably the ones with the simplest associated vertex operator algebras. They're just Virasoro minimal model vertex operator algebras. So in particular, the Virasoro minimal models are labeled by coprime P and Q bigger than or equal to 2. And you get the series of Virasoro VOAs of the form 2 comma P, where P is an odd number starting at 5. These are the non-unitary ones. 2 comma 3, of course, is the Ising model. And then starting at 2 comma 5 and higher, you have non-unitary, with 2 comma 5 being the Lie-Yang CFT. So that's great. Those are some of our favorite vertex algebras, if you have favorites. Then you go to another class of these Argyros-Douglas theories, the so-called A1d odds. And here you run into theories where the vertex algebra is just, quote unquote, just an affine Kac-Moody vertex algebra. But you get some interesting, funny, negative rational levels. So the level of the Kac-Moody for the A1d 2n plus 1 is minus 4n over 2n plus 1. You can write minus 4n over 2n plus 1 as minus the dual Coxeter number of SU2, which is also known as 2, plus 2 over 2n plus 1. And by virtue of that expression, one can recognize, if you've run into the term before, these as what are called Kac-Sawakimoto admissible levels for these affine Kac-Moody vertex algebras. I'll say more about that in a bit, but these are some sort of nice levels, if you want. Before I say more, I'll just say that these have a name because they're nice. On the other hand, if you go and study maybe the simplest superconformal gates theory in 4 dimensions, which is SU2 gates theory with 4 hypermultiplets in the fundamental, then you get, again, just an affine Kac-Moody vertex algebra, in this case, at level -2. -2 can be written as minus the dual Coxeter number of SO8, which is 6, plus 4. And by virtue of that, if you go look up the definition, this is not a Kac-Sawakimoto admissible level. And so whatever was nice about the admissible levels, this is less so. So we're getting maybe less and less nice in terms of what you can go look up in the textbooks. You should, of course, ask about n = 4 super Yang-Mills theory with the simplest gauge group, which is SU2, simplest interacting gauge group. And in that case, I already said that you get necessarily by some sort of translation of symmetries, you get a small n = 4 super Virasoro. But in this case, you get exactly that and nothing more. You get small n = 4 super Virasoro, where the central charge is -9. It's a sort of interesting value of the central charge for reasons that we won't explore today. And then just to jump all the way to very complicated.
I'm sorry, Chris, but what's can we go back to the n = 4 example? So you have gauge group SU2. Yeah, why SU2? Why? Yeah, I'm a bit confused. Should there be also some? I don't know. This super Virasoro. Does it have a modular space? This vertex algebra on the right. Meaning that deformations corresponding to marginal deformations of super Yang-Mills.
It does not. I haven't gotten to this statement. I may have managed to forget to write it down anywhere, but it is a. It should have been. Yeah, this should have been the last thing before, in between the previous page and this page. There is a. I'll write it. I'll write it.
So somehow when we go to
there's a non-renormalization theorem. That controls the VOA 2-point and 3-point functions, and by virtue of that, all point functions. So when your 4-dimensional theory does have marginal couplings, you will not see it in the vertex algebra. Okay.
And the fact that the gauge group had to be SU2, this somehow was a particularly simple case. Why is
it's a particularly simple case. So at higher rank gauge group, you're again going to have structurally always this small n = 4 super Virasoro with whatever the appropriate central charge is that you compute by this -12 multiplication. But then you're going to have additional generators in the generic case. Okay. And the fact that you're going to have additional generators, if for no other reason, if you start doing the calculations, you convince yourself quickly, but it follows from this fact that generators of the Higgs branch chiral ring are always strong generators of the vertex algebra. So at higher rank, you have bigger and bigger Higgs branches. And so you have more and more generators of the ring of functions on those Higgs branches. And so you have more and more strong generators.
Okay, thanks.
Chris, can I also ask a related question about n = 4? So
yeah.
So suppose I don't know it's super Yang-Mills, but I just know that it is like n = 4 supersymmetric theory. So, I mean, you know, I'm thinking about let's say some putative dual of pure gauge supergravity in 5 dimensions, something that only has the stress tensor multiplet as the lowest single trace operator. So would you know what would be the, I guess it should be similar to super Yang-Mills at large central charge for large n. Would you know what would be the VOA in this case?
What would be the VOA in the hypothetical case that might not exist?
Yeah. I mean, you know where I'm going, right? I wanted to understand.
Yeah. No, I know.
You can use this to exclude it.
Yeah. Yeah. So I think the thing that you would be looking at in the case that you just described, I think, would be you would be trying to kill the idea of having small n equals 4 super Virasoro at some large value, some large negative value of the central charge with no additional generators. I think that's the most likely guess. I mean, you should be more conservative. You should ask how many I mean, do you really want to only consider the case where it's something that looks like the theory without the sphere, including 1 over n corrections, or can you have?
I could allow for other operators, but that would also grow, would have like maybe dimension also growing in the central charge.
Yeah.
So maybe I could have other generators, but not, maybe of large dimension.
Yeah, I think this is a nice question. I'm pretty sure that it's something that that Leonardo has given a bit more thought to than me. I don't have a sharp answer. I'm because he hasn't announced it yet. I assume Leonardo didn't complete the argument to kill the possibility of the pure ADS5 theory, but yeah, that's the sort of thing where you would want to leverage as many tools as one is eventually going to build to sort of ask what sorts of self-consistency conditions these things are supposed to obey. Of course, there is a small n equals 4 super Virasoro VOA for arbitrary negative central charge. So you're going to need to have some additional opinions about what sorts of nice properties these vertex algebras should have if you're going to start ruling out things like that. But that's certainly the sense that I think I and other people who spend time with these things have, is that these are non-generic. So I'll say more about this, not in this example, but in a different example later, if I get to it. But this is not a generic level for small n equals 4. So at c equals -9, if you take sort of the generic Virasoro VOA, which exists for all central charges, and you tune to c equals -9, then there are some null states there that there are states that become null there that were not null at generic central charge. So you should quotient out by them to work with the simple VOA. And once you do that quotient, you can't move away anymore. So even though sort of at the level of a phrase, small n equals 4 super Virasoro is something that exists in a family, the vertex algebras we run into tend to not exist in families because they live at special values of parameters where you've quotiented by things that can only be quotiented at those values.
Can I also ask a question about this list?
Yeah.
So how much of it is actually computed and how much of it is like accept? So for instance, in the minimal model case, do you have access to the central charge and also say you see all the truncation of the OPE, or is part of this construction conjectural? Like could it be that you only get part of the spectrum of the minimal model?
I think I have an answer to your question, but can I ask you to expand a little bit on what you meant by part of the spectrum of the minimal?
I mean, just say because when you were showing the OPE of the stress tensor with the local operator, you were looking at quantum numbers, but it didn't seem mandatory. For instance, that if you have a Virasoro primer on the left, you get the same primer on the right, so that it's not clear to me if all these things like are computed, or if you get part of the picture, say the central charge, and then you say, okay, at this central charge, then your P must close within the cuts table. And yeah, I just would like to ask if everything in the, like you get the full minimal model, you get part of the representations, and then you say, then there must be also the others, but we don't know how to.
When I say when I say minimal model, sorry, you're never getting the stuff outside of the chiral algebra in this story.
Okay.
So I mean, you never generate, even in honest 2D CFT, if you start out with the meromorphic stuff, you don't generate the non-meromorphic stuff.
Right. So in this case, like for instance, in the minimal model, what you see the vacuum module.
It's the vacuum module.
That's it. There's no way to add something in the 4D theory so that it gives you the other modules of the minimal model.
So, okay, there are two things you can try to do. There are two different directions you could take that question. One is, given that you have this vertex operator subalgebra, could it be that there are other things that are still a part of the sort of canonically defined associated vertex operator algebra, but that when you do the sort of Virasoro decomposition, they sort of live as modules over that? This, in these examples, is, I think I should be cautious because I don't think I've ever gotten around to checking it for the general case, but at least for the low values event, you can't. These are sort of non-extendable vertex operator algebras in the sense that you can't add additional stuff and then have the whole thing still be a vertex operator algebra. And that's precisely because the modules for these guys have non-half integer dimension. And so they can't live in some, you're not gonna get something that lives in a vertex algebra. You're gonna actually be starting to probe sort of the full 2D CFT structure. There's another question which one should ask, which is, nevertheless, if I have some interesting representations of these vertex algebras, I spent part of last Friday talking about sort of module categories. If I have interesting modules, do those do anything? Just is there any way of cooking up a situation in 4D where I see that structure? And there the answer is yes. I don't think it's a finished story, but if you have, let me draw a little picture. If you have, here's my Z bar plane that lives inside of R4. Here's the origin. If I have a half BPS surface defect in my 4-dimensional n equals 2 theory, and I consider a configuration where it's extended, this is drawn as a line, but this is really the W bar directions. So if I consider a surface defect which lives at a single point on this plane that I've singled out by my chiral algebra construction and then fills the other directions, if I have an n equals 2,2 surface defect, so one that preserves the 2-dimensional 2,2 superconformal algebra in its presence, then by sort of general arguments, that thing is going to be something that you can hit with operators in the VOA and get something consistent. It's compatible with this Q cohomology. And so that thing is going to furnish some sort of a representation for your vertex algebra. This has been, I think, most well discussed in papers by Clay Cordova, Davide Gaiotto, and Shuheng Shao, and then a paper by Maddalena and Lorenzo Bianchi. I hope I'm making the right references. Something that, so an interesting aspect of that story is that in the general case, so forget Virasoro minimal models where we understand the representation theory very well. In the general case where the representation theory might not be under such good control, a priori, from this sort of construction, you aren't necessarily getting nice modules. So I had a little bit of discussion on Friday about different sort of levels of niceness that you could ask for a module to have. And in principle, you could have things from this which fail a lot of the niceness conditions. They could have unbounded below conformal weight spaces. They could have infinite dimensional weight spaces. None of those are in contradiction with general principles that we know of at the moment. So in the case where your vertex algebra has sort of wild representation theory, it's an interesting question how to sort of organize the representation theory in terms of defects. In the case where your vertex algebra has very nice representation theory, like Virasoro minimal model cases, then there's literally only a couple of things that you can get, and so you'll get one of those if you have some way of concocting one of these defects.
But you're not guaranteed to get all of them from this construction, to get all the representations which are allowed.
I don't know of a way to argue that you're guaranteed to get all of them. I could imagine there being a story that allows you to say that if you get one, then you get everything that appears in its fusion products. Although I don't know how to actually rigorously say that you do that. Okay, nice. And again, in these less nice cases, even, I mean, what you mean by all is a little bit up for discussion. Because in some of these cases, you have sort of continuous families of modules, and depending on what category you're working in, you might sort of quotient by various equivalence relations. So it gets a little bit messy, even to phrase the question.
Thank you.
Okay, and then to just finish off this list with one that nobody has any intuition for, except for, I think, like me and a few people I know. But just to show that you actually, in sort of reasonably general settings, get sort of a lot of junk. There's a theory called the genus 2 class S theory of type A1, which is really just a particular SU2 cubed gauge theory, but it shows up in the class S world. And the associated vertex algebra for that is a vertex operator superalgebra. It has fermions with central charge -26, and it has all these generators. So these are strong generators. So it has an abelian U1 current, it has a stress tensor, it has a couple of extra B hat generators, which aren't conserved currents. It has lots of fermionic generators living in these D and D bar multiplets. It has generators that live in, sorry, this keeps trying to erase on me. It has generators that live in C hat multiplets that are not the stress tensor. So to a certain extent, I think this should be thought of as indicative of the generic case, which is that you have a lot of stuff, and just knowing the affine currents and the stress tensor and maybe any extra supercurrents still leaves a lot to be ascertained. Okay. How am I going to do this? Okay, I know what I'm going to do. Okay. So let's look at an example in a little bit of detail that I think illustrates some meaningful points. So in the list I had before, there were some strongly rational C2 cofinite vertex algebras. These Virasoro minimal model cases were example, but most of these things didn't fit into any of the good classifications I gave on Friday about rational, regular, C2 cofinite, etc. So let's look at an example which is not good in any of those ways. I'll take the first one of these A1, I should have made this A1d3. There's an exceptional isomorphism between A3 and D3, but this is the first in my A1d Odds series I had before. This theory has another name, which is the rank 1 F theory SCFT of type H1, if one is familiar with the F theory construction of low rank SCFTs. What do we know about this thing? a priori. So let's get somewhere without doing a whole lot of work. The 4-dimensional central charge is a half, which gives us a 2D Virasoro central charge of -6. And it has an SU2 flavor symmetry with 4-dimensional flavor central charge 8/3, which gives us a SU2 affine current algebra with level -4/3. And already from that, we can make a little numerological observation, which is that this value of the Virasoro central charge, -6, is equal to the so-called Sugawara value associated to that affine Kac-Moody algebra, which is k times the dimension of the Lie algebra over k plus the dual Coxeter number. So if you plug in -4/3, 3, and 2 for those numbers, you get -6. And that means that if I build the Sugawara stress tensor, or the Sugawara vector, which is this quadratic normally ordered combination of my affine currents contracted with the Killing metric up to a normalization, then that thing, just by pure brute force vertex algebra calculation, necessarily generates a Virasoro vertex operator subalgebra of whatever I've got with the correct value of the central charge. A tiny bit of argument is needed at this point, which I won't supply here, but I claim it can be supplied, which tells you that on the basis of that coincidence, you can actually conclude that this object that you build in the vertex algebra is in fact identical to the canonical stress tensor that we got out of our sort of intrinsic construction. And so we're going to have something which has this thing. This is the notation you'll run into in the math literature. This is the vertex algebra associated to the Lie algebra SL2 at level -4/3. And that thing is necessarily showing up as a subalgebra. And in fact, I won't make the argument here, but in fact, we can identify the two. So the vertex algebra that we're getting is exactly this level -4/3 SL2 affine Kac-Moody. And as I mentioned before, this is an interesting level, an interesting / nice level based on work that has been done in sort of the Lie theory world, which is that this level is a Katz-Wakimoto admissible level. And that means that even though this is not one of the vertex algebras you would normally run into in connection with rational conformal field theory, in RCFT, you would be looking at the case where k is in the natural numbers. Those give you the so-called integrable representations. I should say k is not in that in this case. Nevertheless, the characters of a good class of modules that I want to define for these vertex algebras obey some modularity properties, which are reminiscent of the sort of modularity of characters that you have in RCFT. So the modules of these things are going to converge to functions of tau. Remember that we have q is e to the 2 pi I tau. And let's say that we have x is e to the 2 pi I z. And we're looking at the trace of q to the L naught minus c over 24, x to the j. Not x measures charge under the carton of my SL2. So your characters converge to functions of tau and z that transform nicely under the modular group, meaning that there's some sort of weak Jacobi forms, actually weak Jacobi forms of weight 0. That's not important, but there's some good modularity property akin to what you run into in the rational case, even though these are not rational. Okay, so we're running into irrational vertex algebras that still have some niceness properties. They're not only irrational, but they're not C2 cofinite, which was this condition I mentioned last time is sort of often taken as a stand-in for rationality, although it's a little bit weaker. To see that these things are not C2 cofinite, let's look at our vertex algebra, we have generators that I'll take a basis for SL2, which is Chevalier basis. So we have J plus, J minus, and J3. You can build a set of operators which just look like iterated normal ordered products of J plus. Those things are related by the state operator correspondence to the states I get by acting with J plus -1 over and over again on the vacuum. There's obviously an infinity of such states for any n. They have J3 charge n and conformal dimension n. And in fact, they're the unique states with J3 charge equal to their conformal dimension. And so either those states are there or they're not. They can't be related to some other states by some sort of null relation. And so they're there unless if I compute the norm of one of these states, I get 0. And famously, when I compute the norms of these states, I only get 0 if k is a positive integer. That exactly gives me these integrable levels, of course, that I run into in WZW models. So in my case, because k is not a positive integer, these things are all non-zero. And so this gives me an infinite set of states which are manifestly not in this C2 subspace that we met on Friday. Remember, the C2 subspace was anything involving derivatives. And when I write this thing down, there's no derivatives in sight. So this is giving me an infinite set of things that don't live in the C2 subspace. And so when I define the C2 subalgebra by quotienting by things involving derivatives, I'm going to get something which is infinite dimensional. Okay, so this is not C2 cofinite by direct calculation. But it does have some structure that is visible at the level of this commutative C2 algebra that we met last time. There is a null vector, or well, there are many, but there's a primitive null vector that you can just go look for. You can start computing 2-point functions and look for something that has 0 2-point function with everything else of the same conformal dimension. And it's this gadget. Normal ordered product of an arbitrary one of your currents with the Sugawara vector. Then with corrections that, of course, involve derivatives. And so I'm planning on ignoring them if I'm talking about the C2 algebra. And so sure enough, in the C2 algebra, forget this. This is a relation that says that the Sugawara guy in the C2 quotient times the current is equal to 0. And that gives me a characterization of my C2 algebra like this. So I start out with a commutative associative algebra generated by variables in one-to-one correspondence with the strong generators of my vertex algebra, the currents, J1, J2, J3. And then I have this null state, which looks like J1 squared plus J2 squared plus J3 squared up to normalization. That's the Sugawara vector, multiplied by an arbitrary one of the JAs. That's an infinite dimensional ring, but it has some structure to it. It's notable for my purposes that this is an unreduced ring, meaning that it contains things that are nilpotent. In particular, if you take J1 squared plus J2 squared plus J3 squared, the Sugawara vector, and you square it, then you're going to get 0, because as soon as you multiply J1 squared plus J2 squared plus J3 squared by anything, you get 0 by this relation. And that means that if you're thinking of this as a ring, which if you're thinking of this as these relations as something which cut out a subspace in affine space. So if I look at the subspace in C3 cut out by these relations, it's the same thing as the subspace that's cut out by a relation where I set J1 squared plus J2 squared plus J3 squared equal to 0. The extra elements of the ring that I am ignoring if I'm setting this equal to 0 are nilpotent, and so they can't have an expectation value. They can't take non-zero values at any points. And so if I take that C2 algebra and I reduce it, meaning throw away everything which is nilpotent, then I get a slightly simpler looking thing, which is the ring generated by J1, J2, J3 with just this quadratic relation. And it happens to be a fact that that thing is exactly the Higgs branch chiral ring of my four-dimensional theory. So this is the ring of functions on the space C2 mod Z2, which is also known as the minimal nilpotent orbit of SL2, which is also known as just the nilpotent cone of SL2. There's various ways of saying it, but this is a nice space which is already associated to my four-dimensional theory, and I've sort of found it at the expense of having to throw away some stuff. So this has been a story that I just sort of conjured, but this allows us to connect structure that we care about with structure which is canonically defined and already a part of the formal theory of VOAs. So if you take the algebraic variety defined in the way that I just did, by taking the C2 algebra and throwing away nilpotents, that's been called the associated variety. It was defined, oh, I should have put it down here. It's defined in this paper by Arakawa and Kawasetsu. This is a fancy way of saying the same thing. It's saying that the associated variety as an algebraic variety is what you get when you take this ring. And okay, M-spec is a fancy way of saying that you throw away the reduced things and think of it as defining you a subspace of affine space. And so in this example, by direct computation, I have that the associated variety, which is a canonically defined thing in a vertex algebra, is the same thing as the Higgs branch of the underlying SCFT. And in fact, we might already know this about minimal nilpotent orbits of SL2, but without going into the details, it's true on general grounds that the Higgs branch of a four-dimensional n equals 2 SCFT is always not only some algebraic variety, but a symplectic variety. Whereas this associated variety, on the basis of the little derivation I gave last time, is only generally guaranteed to be a Poisson variety. So it's guaranteed to have a Poisson bracket on its functions, but the Hamiltonian vector fields generated by the Poisson bracket may not span the tangent space at every point. And so this is a special property for a vertex algebra to have, that this canonically defined algebraic variety that's only sort of guaranteed to you by God to be a Poisson variety actually is a symplectic variety. And in this paper where they introduced the terminology, Arakawa and Kawasetsu dubbed a vertex algebra with this property quasi-Lie. The history of that name is a little funny, but let's not worry about it. It means this state of affairs that I just described. And more importantly, they proved a theorem which connects back to this, this Katsuaki-Moto admissible level business, which is that quasi-Lie-ness of a VOA, having the associated variety be symplectic, is enough to guarantee that your characters have some modular properties. Again, I'm not quite putting a fine point on the modular properties because it takes extra lines to write out what I mean, but they obey some non-trivial modular properties. There's some sorts of modular functions of a type that you wouldn't have generically, but are a little bit reminiscent of the RCFTs. Okay. I will pause for questions and to say, I think I can finish in the next 7 minutes by only 20 minutes after my official endpoint. I'm actually the host, so I don't have to ask anyone for permission. But just a warning to everyone that I think I'll finish up in not too much longer.
Actually, Chris, I'm sorry, but I claimed back the hostship. I actually.
Oh.
But you can go ahead a little bit, yeah.
Okay.
But first questions, yeah.
Okay, no questions. So I want to probe a little bit what's going on with this, with these calculations I just described, where I computed one thing and then there were nilpotents, I was throwing them away. Can we understand a little bit better the relationship between the different objects I've been talking about? And this is one of these cases where it helps to go under the hood and think about the underlying construction in 4D. So let's look at the relation I've claimed that we have earlier, which is that the stress tensor, the sort of canonically defined stress tensor that I get from 4D, is supposed to be identified with the Sugawara construction, where you notice an R-charge mismatch. So the Sugawara construction is built out of bilinears in the affine currents. The affine currents are B hat 1 multiplets, so they correspond to operators with R-charge 1. So naively, things that are quadratic should be sort of morally things with R-charge 2. But the stress tensor lives in the C hat 0 multiplet, and the associated Schur operator has R-charge 1. So there's a little bit of an R-charge mismatch in this relation. So what's going on? Well, in the Higgs branch chiral ring, in the actual commutative algebra just of the B hat 1 multiplets, when we don't have this funny twisted translated business involved in moving them around, I have this relation that I described before defining the Higgs branch on the nose. So there I have sort of the expected quadratic relation, just at the level of multiplying B hat 1s without any R-charge violation. In the VOA, if I'm going to get the stress tensor appearing in this object, it's going to come because when I do the normally ordered product, what I'm doing is taking two of my operators. Let's say one is at the origin, and so it's in its SU2R highest weight. And then I have the other guy displaced, and so I actually have either the SU2R highest weight or the 0 or the -1 guy. And in order to get something with R-charge 1 on the right-hand side, I have to be looking at the guy that has R-charge 0. So I've picked out a particular component in the twisted translated expansion of this B hat 1 operator. And in that OPE, I'm going to be getting a copy of this Schur operator associated to the stress tensor in the singular OPE with a 1 over Z bar, but that 1 over Z bar gets canceled by an explicit Z bar that secretly lives in front of here, according to my translation prescription. So I sort of have a relation, which at the vertex algebra, I don't quite see it. And that's because where I'm supposed to have a 0, I get something that gets filled in by sort of a quantum correction associated to my funny rule for moving things around, which is related to the non-commutativity of the vertex algebra. So the stress tensor is filling a gap, which is there in the Higgs chiral ring. And I don't see it in the vertex algebra when it's presented in its own right, because I don't see SU2R charge in the vertex algebra because it's violated by this twisted translated construction. And so there's a hint from this example that there's some sort of additional structure that I should want to elucidate in these vertex algebras related to the fact that there's this underlying SU2R charge, which isn't preserved, but it sort of organizes my space of states. So let me define the structure associated with that, which lets us really make a very precise technical conjecture associated to this Higgs branch story I was telling before, and then I'll be done. So what I get as a consequence of there being this underlying grading, right? My space of Schur operators, I said at the very beginning, is a triply graded vector space. But my OPE doesn't preserve SU2R charge. It's not covariant in any way with respect to SU2R charge. However, my rule for moving operators around is that when I move it around, I only lower R charge. I don't raise it. And so that means that when I take two operators in this vertex algebra construction and take their OPE, although SU2R isn't conserved, an associated filtration is conserved, meaning that if I take a graded component and include all the lower graded components, then I'm going to sort of land in that. So this is defined this way. You define a filtration, you define the sort of R filtration, as we call it, where the Rth component looks like the sum of all of the graded components of your Schur algebra, where you take SU2R charge to be your given value or any lower value. And this is a filtration in a technical sense. If you go look up filtration on Wikipedia, you'll see this sort of an expression for an ascending chain of subspaces. And this filtration interacts well with the OPE in a way which is somewhat reminiscent of what we were seeing in the C2 story on Friday. In particular, normal ordering preserves R charge at the level of filtration. So if you take something with R charge less than or equal to R1, normal order with R charge less than or equal to R2, you get something with R charge less than or equal to R1 plus R2. And similarly, if we define a bracket operation corresponding to the simple pole, just like we did in the C2 story, then again, it's compatible with the filtration at the level of a shift by -1. So the OPE lowers, the singular OPE lowers R charge by at least 1, is what this is encoding. Ignore this box for reasons of time. So in light of this filtration structure, if we define everything but the Higgs branch operators, that's what I've defined here. This is because I have this graded structure, I can go ahead and look at some components of my filtration that include everything that isn't a b-hat multiplet. And it turns out that that thing contains the C2 algebra that we met last time, built out of derivatives. So in other words, you can think of derivatives as sort of taking you out of the running of having a Higgs branch operator. And because the C2 algebra is in this subspace, and we saw last time that the C2 subspace is where the commutator and the associator and the Jacobiator of the bracket and the Leibnizator of the bracket, where those things live, that meant that if you took this quotient, well, if you took the quotient by C2, you would get something that had the structure of a commutative associative Poisson algebra. And that means that if you take a bigger quotient, you still get something that has the structure of a commutative associative Poisson algebra. And this thing comes out as exactly the Higgs branch chiral ring. So if I know how to impose this R filtration structure on my underlying vertex algebra, then I can find my way back to the Higgs branch chiral ring by a quotient that looks very similar to the quotient we were taking in defining the C2 algebra. I'm quotienting by a bigger thing, but the same mechanics are involved. And so what I get a priori is this situation. I have the C2 algebra lives inside of this Higgs complement subspace, where if I take the Higgs complement subspace quotient, I get back the Higgs chiral ring. And just by sort of vector space quotient linear algebra, this tells me that the Higgs chiral ring is a quotient by some ideal with respect to the normally ordered product and the Poisson bracket of the C2 algebra, where the ideal is defined in this particular way. So there's some abstractly defined quotient at the level of the R filtration of an ideal that gets me from the C2 algebra down to the Higgs branch chiral ring. And this lets us make a very particular, precise conjecture, which is nevertheless hard to have intuition about, which is how to characterize this quotient that we need to take to go from the C2 algebra, which is canonically defined, to the Higgs branch chiral ring, which is canonically defined in physics, but not canonically defined for vertex algebras. And the conjecture that Leonardo and I made a number of years ago, which has now stood up to an enormous number of consistency checks, is that this ideal is exactly the nil radical of the C2 algebra, which is, again, the thing just consisting of all nilpotent elements. It has to include it because the Higgs-Cairo ring is reduced and doesn't have nilpotence in it. So I have to at least divide out by nilpotence. The claim is that I don't have to divide it by anything else. And this is something which I think I can confidently tell people who care about this stuff that you should believe. It's really passed a lot of tests. But I don't actually think that we're particularly close to having a proof of it. And I think that to prove it would require some new ideas, probably involving going back to sort of full four-dimensional OPE reasoning in arguing about what this no-potency condition would really mean in sort of a bigger Bootstrap setting. So if this is true, it implies precisely the modularity condition for the Schur index that follows by this theorem of Arakawa and Kawasetsu. And that's then sort of a weak check that you can do in the sense that now if you go and find your favorite family of 4D n equals 2 SCFTs, a consistency check of this conjecture is that those Schur indices will be modular in this weak sense that you can read a definition of in Arakawa's paper. And that weak check has been performed really in an overwhelming number of cases. Even the sort of nilpotency check is something that we've seen in a whole lot of examples. So I've, I think, taken advantage of people's patience quite a bit, so I'll wrap up. I won't summarize what I've said. It would take me another hour because I talk a lot. But I will summarize things I didn't say, which are, there's some sort of big topics in the subject. I ended up talking about this, so I'll skip it in response to Marco. But of course, there are lots of theories where we have a Lagrangian description in terms of gauge theory. And so there should be some story about describing these vertex algebras when you do have a Lagrangian description. And there is a nice story in terms of a sort of BRST construction that then leads to a nice class of cohomology problems to try to verify some of the conjectures that have emerged about how to describe vertex algebras associated to given theories as strongly finitely generated vertex algebras. There's an emerging story about free field realizations, which is that it appears that amongst the other nice properties of the vertex algebras coming out of this game is that they admit constructions as subalgebras of relatively parsimonious free field vertex algebras. And in that description, you actually get the R filtration back. So a lot of this mystery about R filtrations and connecting with the Higgs branch becomes transparent if you have one of these free field constructions. And finally, something I should have mentioned in lecture 1, but I don't think I got to it. The guts of the construction in terms of this Q cohomology only depended on having an SU1,1/SU1,1/2 subalgebra in n equals 2. This is the sort of maximal subalgebra that we used that acted on the ZZ bar plane. And so you have an immediate sort of transposition of this story to any situation in other numbers of dimensions with other amounts of supersymmetry, where you have that same sort of superconformal algebra structure. And indeed, you get a construction exactly in the cases of 6-dimensional theories with 2,0 supersymmetry and 2-dimensional theories with 0,4 supersymmetry at least, where you're going to be able to run the same machine and get a vertex algebra with the whole twisted translated story, and you can try to understand as many examples in those cases as you like. We've worked out, I think, most of the story that's relevant in 6D with Balt and Leonardo. The 0,4 case is not well explored. So thank you for your endless patience, and I'll take any questions before people take a break.
Thanks, Chris. Are there any questions?
It may not be related to your lectures, but can anything be said about n equals 3 superconformal theories?
In 4 dimensions.
Sorry?
Do you mean in 4 dimensions?
Yeah, I'm 40. Yeah.
So the thing that I know how to say structurally is that the Virasoro sector will automatically be enhanced to an n equals 2 super Virasoro. Of course, people have done work on sort of enumerating interesting classes of n equals 3 theories, where you could ask about the associated VOAs there. And a fair amount of work has been done, and I am completely blanking on the right references to give, so I will give none at risk of offending someone by being selective. But I don't have, at least I don't have sort of a deep thing to say. You can think of them as special cases of n equals 2, where the additional ingredient is that you have this extra n equals 2 super Virasoro. But there's probably something more and smarter to say, but I don't know it.
Thank you.
Can you, Chris, can you like outline what would be the dream in this field? What would be the final lofty goal towards which this is all going? What would you like to establish?
You want a lofty goal that I think will happen, or just, I mean, I would say the lofty goal is that one can collect enough non-trivial sort of extra structures that these algebras are supposed to obey, on top of sort of the basic things I've described. So already this quasi-least condition, although it looks quite technical, it's a strong condition. If you have a Virasoro algebra, if you have an affine-Kac-Moody algebra as your whole vertex algebra, you're cut down from sort of all generic values of levels to special values of the level where these things are quasi-least. There's an additional story that is the thing that I skipped over at the end, which is still very much work in progress, so maybe it's good that I skipped over it, which is to incorporate the fact that the 4-dimensional theory is unitary, which, even though these vertex algebras aren't unitary in the superficial sense, because you would say, I know what unitarity means for a Virasoro algebra, and these ain't it. Nevertheless, there's a sharp structure, which is sort of the version of unitary that you get from 4D, which is a kind of positivity property on inner products, except that you need to be very detailed in defining the inner product. And we have lots of very partial results, I should say. So I've been working on this with Leonardo and with his student Gunan Schmugel. And of course, we know that there's sort of very strong constraints on unitary vertex algebras with various sort of rationality conditions. So I would say that the sort of big dream, although I don't have a roadmap, is that there's going to be enough structure here that you could start thinking about some kind of classification program. I mean, it's always a little bit, I think, cheap to say the end goal is classification, because I don't know how much classification of 4D n equals 2 SCFTs should really be the target. But I think that sort of having that as a motivating factor might put you in position to start answering the questions like Joao was asking. So say you have an n=4 theory. Does just the, I mean, if we can compile enough structures that have to be present at the level of the associated vertex algebra, could you go classify the n=4 super Virasoro extensions that satisfy those conditions and reproduce the expected classification of super Yang-Mills theories? That's something in that sort of ballpark is where I think the most meaningful sort of physical targets are. I have the luxury of currently being employed in a math department, and there are a whole extra collection of interesting questions about these things just from a mathematical point of view. Vertex algebras are the subject of a lot of work. They show up as sort of organizing principles in different geometric representation theory problems, and the things that are coming out of these 4D setups seem to be right in line with where the most interesting work is in this as a purely mathematical subject as well.
Okay. Well, unless there are any other questions, let's thank Chris. Thanks a lot, Chris. I enjoyed very much. And we have a break, and then we resume in half an hour with Andrea Guerrieri. Cheers, everyone.